In this video, I'm going to show you some shortcuts for calculating the residues of complex functions. And this corresponds to problems that you had on graded homework 6. So I'm going to give you a little bit of theory and then I'll give you the shortcuts. So first of all, suppose that f of z has a simple pole at z naught. Then that means that its Laurent expansion would look something like this. With the simple pole, I just have one term on the left with z minus z naught on the bottom. And then I have a regular Taylor series over here to the right. And so forth. So remember, a simple pole is a pole of order 1, and that means that the biggest power of z minus z naught in the denominator is just the first power. Now the residue is always this term, which I'm labeling b1. It's going to be the coefficient of z minus z naught to the negative 1 power. So let's see how we could recover this without having to develop the Laurent expansion. First of all, let's multiply both sides of this by z minus z naught. So z minus z naught times f of z will be b1 plus a naught times z minus z naught plus a1 times z minus z naught squared, and so forth. And in order to get b1, I could simply set z equal to z naught on the right side of the equation. That'll make this term disappear, make this term disappear, and so forth. The only catch is, on the left side, z minus z naught times f of z is usually an indeterminate form. So instead of just being able to plug in z equals z naught, we usually have to take a limit. So we end up with the limit as z goes to z naught of z minus z naught times f of z is equal to b1. So the takeaway for this is, for simple poles, the residue of the function f of z at z naught is equal to the limit as z goes to z naught of z minus z naught times f of z. I'll give an example in a minute, but let me show you next what happens when you have poles of order 2. If it's a pole of order 2, then, as usual, on the right side, we have a naught plus a1 z minus z naught plus a2 times z minus z naught squared, and so forth. But over on the left, I have b1 over z minus z naught, and I also have a b2 over z minus z naught squared. So this is what it means to have a pole of order 2. Now the residue of the function is still b1. So we want to figure out a way of capturing b1 without having to develop the Laurent series. This time, let's multiply both sides by z minus z naught squared. On the right side, that'll give me b sub 2 plus b1 times z minus z naught plus a naught times z minus z naught squared plus a1 times z minus z naught cubed, and so on. And I'm still trying to get my hands on b1. So here's the clever trick. Let's differentiate both sides. If I take the derivative, this b2 is going to go away. So I'm going to take the derivative with respect to z of z minus z naught squared times f of z. And on the right side, the b2 is gone. I'll have b sub 1 times 1 plus, differentiating using the chain rule, 2a naught times z minus z naught to the first plus 3a1 z minus z naught squared, and so on. And now, here's that b1 that I want. So I can simply set z equal to z naught on the right side. The b1 stays where it is, and all these other terms become 0. Again, on the left side, this might be an indeterminate form, so we might not be able to set z equal to z naught directly. So instead, I'll need to take the limit as z goes to z naught of the derivative with respect to z of z minus z naught squared times f of z. And that will give me b1. So the takeaway here is going to be that for poles of order 2, the residue of f of z at z naught is going to be the limit as z tends to z naught of the derivative with respect to z of z minus z naught squared times f of z.